And Lille.
And in Lille. I know the
I
Lille.
have.
Oh, Ben has also.
Yes.
Yeah, I have.
I'd like to welcome you to this to the session on molybdenum carbides and related materials. When we put together the program on molybdenum catalysts, we wanted to have one session to focus on something other than molyoxides and molysulfide, and this is it. And it's really, and we're grateful to the people who have contributed papers, both theoretical and practical, and grateful to Marc Ledoux for accepting the invitation to give the keynote speech. Now, in the usual tradition, I'll introduce Marc perhaps with a little more detail than the other speakers, since he's the keynote speaker. I've known Marc for many years. He's really a very eminent French scientist. He's director of research at the CNRS in France, and he kind of commutes between Strasbourg and Lille. He's director of the Materials, Surface and Catalysis Laboratory in the Louis Pasteur University in Strasbourg, and he's director of the Catalysis Laboratory in Lille. 200 papers, 20 patents, and he's the director of a company that is commercializing silicon carbide for catalyst supports. And Marc, well, that's what it says here, Marc. You emailed it.
Scientific director.
Scientific director, sorry. But I'm going to end up by saying Marc is a kind of a bit of a renaissance man, because he's also an economist. He's involved in research in economics in Strasbourg. The impact of research on the economy, which seems to be an entirely appropriate subject for economics research. Marc, it's a great pleasure to have you here. I'll now ask you to present your keynote presentation on high surface area, molybdenum carbide and derivatives. Thank you very much.
Thank you, Philip. First, I would like to thank Molybdenum Climax, a new name I've forgotten, excuse me, and particularly Alan Armour and Canada plus Philip to invite me for this meeting. I have a very difficult succession today because after the show of Philip yesterday, don't expect from me so many jokes. But I have the result of the British election. It was a wave of the Labour Party. I see that this morning. So I think that all the cow diseases you have in your country has not affected too much of crime this year. Well, in France we are much more at the moment interested by football than by election. And by the way, we beat Brazil yesterday again. 2-1 in semi-final. Well, yesterday we had a very nice presentation by Philip. Oh, what's going on?
Change the configuration, the resolution.
I did not.
On the
It was working perfectly well before. Wait, I will close it and reopen it. Shall we see?
Sorry, Marc, I think we'll be the technical person. We'll see if we can sort out the projection.
Maybe the second picture is better. Well, okay.
Where are you going to see half?
You have to see all my slides.
Where are you going to see half?
On their way.
Where are you going to see half of each slide?
But the half hour is valuable.
That's Mr.
So you're finished.
That is Mr. This is Mr. Bill Gates. Another reason to put him in jail.
With the TV.
It was working perfectly well this morning. Now it has been again. So you can That's the other lecture I've done this year.
Mark, you have to change the resolution.
But I can't. I'm a Mac man. I'm not a...
You can change it. I'm a Mac man.
This is slightly unexpected. This is a Macintosh expert.
Normally what I do, I just push that and put it in. Sorry.
It was you to
I didn't touch
you.
it.
But it was enough, you know, it was sufficient.
Yes, I was saying that yesterday Philip made a long explanation about the role of these four elements, carbon, oxygen, sulfur, and nitrogen binding molybdenum. Obviously, I will just give some words on carbides, but as you know, carbides are a little bit too much active. It means that they destroy everything when you put a product on them. They crack everything. And one thing that Philip did not say yesterday, that it is the unions of these elements which can be very interesting. And I will focus today more on oxycarbide of molybdenum, where we have done quite a lot of work in the last 10 years. And it is that I would like to talk about today. So, but first, before that, a quick history of carbide for catalysis. So obviously it's a group of Michel Boudard, and Michel Boudard himself was developed 25 years ago, this interest for carbides in catalysis. And he has, the big problem with the carbide at this time was that the carbides only exist with very low specific surface area because of the ways they were prepared. And the great thing that they did was to prepare carbides by temperature program carbon reduction of oxide, sorry, or via nitrides, in order to develop high specific surface areas materials. So then you had other people, particularly Taylor-Yama, but coming also from the group of Michel, who has made other carbide synthesis because the group of Boudard mainly focused on molybdenum and tungsten. And then in the course of this work, other people working still with Michel, and it's Michel Leclerc or Enrique Iglesias or Lee or Ribeiro, who in their research on carbides found sometimes oxycarbides in their studies, and particularly Ribeiro found very interesting oxycarbides. We'll come back on that later. And finally, well, there are many other people who are working on carbide, and sorry I put my group here, because we have developed a new method to prepare these high specific surface area carbides. Instead of using oxide, a metal oxide, and attacking this oxide by any sort of carbon molecules, hydrocarbons, mainly hydrogen, plus hydrocarbons, we have done the reverse. That means that we start from a carbon form, and we attack this carbon form by a vapor of oxide or a liquid of oxide. We call it a shape memory synthesis because very strangely and very interestingly, the original shape of the carbon is maintained during this synthesis. That means that we don't need to make any shaping at the end, which is always a problem when you use carbide. So, in fact, all the secrets of these new materials were based on the synthesis. So it was important to prepare stable and active phase, which have a high specific surface area, as I said before. So, for MO, for instance, by hydrocarbon reduction of MO3. So, and there it's all the difference. Do you have a pointer or laser pointer?
Should be in
There's a laser
In that little
Be in the
plastic bag.
plastic bag.
The yellow
it's a
thing.
That's yellow thing. I believe it was a pen, sorry.
Nope.
Okay. That's not Microsoft, but it's even more complex.
Here you go.
Ah,
That
yes.
one. Yep.
Good, thank you. So, and that is all the difference. If you do like a Boudard group, program temperature, that means you start from the oxide and you treat the oxide by increasing the temperature regularly with time, you finish at the end by a carbide. Obviously, all along, these people, and particularly Ribeiro, has found that there were intermediates, which are oxycarbides, but they do not stop really at these intermediates because they wanted to go to the carbide. And for us, as we have done carbides also, and as we have tested carbides for catalysis, and we found that these carbides were not very interesting for the reactions we wanted to study, we were more interested by these intermediates, which could be very stable, but instead of doing a programmed temperature with increasing the temperature regularly, we treat the material at in an isothermal way. That means that we can stop at stable intermediates like some oxycarbides. If you prefer, you have a series of materials starting from MO3 and going to the end to MO2C, and with different intermediates which can be stable. In fact, we have found 2 oxycarbides which are very stable, one which is close to the oxide, the one that we shall talk about today, and one which is close to the oxycarbide, and this one, to the carbide, sorry, and this one was particularly found by Lucien Leclerc and by Ribeiro. So we shall talk to the oxycarbide which is close to the oxide. Well, how we discovered this material, so I will not enter too much in the detail because of time. But if you make this reaction, you take heptane plus hydrogen, and you put that on MO3. And if you wait 2 or 3 hours, you see nothing, no reaction in this condition, strictly no reaction. And progressively, you begin to see a beginning of conversion, as you can see here, slightly going up. But immediately, the isomerization selectivity in C7 branch molecules is very high. You see, you get immediately almost 90% of selectivity. And if you leave time going, and after a day, you arrive at a level where you have a very high conversion and still a very high selectivity. And we shall see at these 3 different steps how the materials has been moving to arrive at this final condition. That will be the first part of my presentation. And then I will go to catalytic reactions. And you will see on different transparencies some references down there, and that's where you will find what I'm talking about today. Well, so we start at this first arrow. So we have MO3. Yesterday we had a beautiful lecture on the structure of MO3, so these transparencies are not as good, but you will understand what I mean. You have MO3 layers. MO3 is a layered compound. There are the cells parameters. And in order to be sure of what we were doing, we have prepared our MO3 by different recooking in order to have highly crystallized MO3, but in selective platelets. You can see that from the X-ray diffraction, where the 0K0 planes are really favored compared to all the others. And that is the scanning electron microscopy pictures, where you can see very nicely these platelets. And the surface area of this MO3 at the beginning is 0.2 square meter per gram. And it's a highly pure MO3 that we have redistillate many times in order to avoid any impurity in it. Well, so now we go to the second arrow. Sorry, I'm going too fast. We are going here, intermediate position. So, as I said, the first step of the hydrocarbon reduction. We are now in an intermediate situation. The specific surface area has been growing from 0.2 to, sorry for the comma, it's coming from a French presentation, to 42 square meter per gram, including 28 square meter per gram of microporosity in this material. And the main facts are, if you look at the scanning microscope, the structure, the lamellar structure has been preserved. So it's the transformation does not change the shape of the materials. And when we look at different parameters that we shall go later, we can see that in fact, after 3 hours of treatment, the only real difference is that we have a shrink of the layers between MO3 in this direction, from this dimension to this one, and at the same time, an amorphization in this direction. And you can see that on this X-ray diffraction. So obviously we have MOO2. A little bit of MOO2 is formed during this carbon reduction. I will not now, enter also in the detail, but it's important to have this MOO2 at the beginning because MOO2 is able to dissociate hydrogen. And it is in fact a self-catalytical process. But what is more interesting, that you have these bands, you can see here, which are in fact, I would say, reminiscent of the MO3 0K0. And as I said here, they are at numbers of 1, 2, 3 of family planes, but with a shrink dimension compared to what we had on MO3. Well, now we move to the third arrows. When we arrive at after 24 hours of treatment, no, sorry, that is still the 3 hours. I was going too fast. That's the problem with this presentation. With the usual one, you look at the next transparent when you are talking on the old one. And there you are surprised like the auditors. That's a little bit of problem you have to learn to use this apparatus. So you see we have this order. So there it's a more, a less focused system. You have a sort of amorphous mass of oxycarbide. We call it already oxycarbide, even if it is not the final oxycarbide. Plus MOO2 crystals. These MOO2 crystals, you can see them very well there, and also by selective area electron diffraction. But this selective area diffraction is made on this carbide. And you see, if you enlarge, if you increase the resolution, you see this very strange shape on it, but it is not the final product. Then we go to the arrows at 24 hours. Well, surface area has increased from 42 to 68. And in fact, I'm not happy with the 68 because the student put back in air. I mean, not in air, but he has neutralized by oxygen this oxycarbide, and that was a mistake because normally you go much higher. You go to 140 square meters per gram. That's not what we go for. And you see also the development of a microporosity. You see that we have preserved the shape, so don't worry with these rods. That's the remains of the silicone wool that we put on both sides of the reactor. And instead of having now a layered compound, after this long treatment, we arrive to a cubic system, which has a parameter of 0.41 nanometers, or 4.1 angstrom. And we wanted to have the structure of this material, and we took almost 10 years, because it's an extremely, to get it, it's an extremely pyrophoric compound, very difficult to make crystals, because it's more or less amorphous, and we have been lucky, and you will see later how we managed to obtain this structure. And that is now what I will try to show you. So if you make an XRD on this final product, you still have the MOO2 different bands, but you have the bands corresponding to this new crystalline structure. I will not enter into detail here. But one thing which is very important, that when you start from MOO3, as I told you, we always get some MOO2 inside. And this MOO2 is necessary to make this phase, because MOO2 is the agent of dissociation of hydrogen, and it is important to have first the formation of a sort of bronze of MOO3 before you introduce carbon. If you do not have this bronze, it's impossible to have to introduce carbon inside. And so, knowing that, we have prepared the bronze, this one, we have prepared other bronze, it works also, and from this bronze, by treatment with an hydrocarbon and hydrogen, we get the pure phase, which is without MO2. And these bands, we have better spectral diagram than this one, but this one is already quite good. And from this XRD this diffraction, and from pictures that we get in high resolution 10, and using a special new software which has been developed by at the University of Paris by a group of researchers in Orsay, you will see the reference later, you can make now the structure without having a big single crystal that we used to do in the past. And that is very interesting, just by doing modelization. And I will try to summarize quickly that. So that is a sample diffraction. What we have. We have, as you see, 5 rays here and 1 here. This one we shall talk about later. So we knew that we have a cubic sample, because when we were looking in the transition electron microscope, whatever was the orientation, we always had these 0.41 nanometers distances. So we decided to fix these distances and then to start to make modelization. First, we took a cubic structure of carbide or oxycarbide, and what we observed that if you take a simple cubic, you have too many bands which cannot be fit with the samples. Then we went to a body cubic, body-centered cubic system. You see, we begin to diminish the number of bands, but still there is no possibility to fit that in there. Then we went to a FCC cubic, like for instance the nitride, MO2M, and what we found, or MO2C, that the bands were all right now, at the right position, which is very interesting. You can see all the bands were there, except this one, but we shall come back on this one later. The only problem was that the intensity of these bands were not correct. And there we found those papers from crystallographs, people who has been working on this sort of structure, saying that in fact the stoichiometry of the light elements, normally we always talk on the heavy elements when we make XRD because they are the most important for the diffraction. But these people have shown that if you modify the stoichiometry, for instance, going from MO2C to MOC to MOC2, you modify the intensity of these bands, and you can, without touching the distance or the angles. And you can see that with the stoichiometry of MOX2, X being oxygen or carbon, you get a very, very good fit of these materials, except this band again. And I think I've put that in the table. Oh, yes, before the. So there is the table, and you can see both distances and intensities are very nicely reproduced by the fit, and that's experimental. And this 200 plane is reminiscent to the 0K0 planes of MO3. In fact, it's a sort of topotactic synthesis of these materials starting from MO3. Well, we did not do only the XRD simulation. The same program, which is the simulation which are made with Carbides crystallography 3.0 made by Boudias and Monceau. There are people from the University of, and I think it's free on the web, this thing. Now, I'm not sure. You can also simulate the selective area electron diffraction made in transition electron microscopy, and you can see that by changing the amount of, or not changing the amount, sorry, by taking out molybdenum from the sites where they should be, in other way, making vacancies of molybdenum in the structure, we finished by a very good fit of this SID spectrum we get, which means that finally the product has a deficiency in molybdenum. This molybdenum oxycarbide has the same structures as an nitride, but instead that all the MO sites were occupied. In fact, it's only one site on two which is occupied, so which corresponds well to this stoichiometry of MOX2 that I have shown before. Now that is to explain these funny bands. You remember we have a band in the spectra, this one, that we could not explain. So there are two solutions to explain that. Or it's a band which remains from the intermediate phase. I'm not going back because it will take too long, but if you look at the intermediate phase after 3 hours, we had a band at this distance, more or less, 0.62. But Tedoyama came in our lab for a while. He was invited professor with us, and he started to look at his crystallographic results, and he's a very good crystallograph, and he found a very nice explanation for this band. If you look at the that is the 10 pictures of this oxycarbide. You see this chevron-like structure, and that is the crystalline structure that I have just described before. And if you make inside this crystalline structure these vacancies of molybdenum, which are these, if you look at the plane in this direction, you get this sort of configuration, which one first explains this strange shape in chevron, but also you have the distance here, which is a new plane, which should not exist if you do not have these vacancies. And that explains why you have this band at 0.615. And I like very much this explanation more than a reminiscence of the phase which would not have been transformed, which was my first explanation. But that was quite a tricky work to do, and thanks to Ted for doing that. Well, and then we were very lucky, because in the course of another study, we were trying to prepare this oxycarbide at high temperature. Instead of working at 350, we were working at 550 degrees, but by flash. And one day, doing microscopy on this flash MO oxycarbide, we found a wonderful picture, that's a lac, where we had a map. That means it is the same crystal, which is twist, and you see this part is look along the 110 axis, and this part is look along the 100 axis. And you can see there the different distances and angles that we have measured there also, and they fit perfectly well with the crystalline structures that we have made by simulation and by measurement before. So that means that now we finally obtain, after such a long time, a real structure of these new materials. And the last thing which was missing was its composition. And there and again, as I told you before, it's a very difficult job because they are so air sensitive that to make a nice analysis of this was not trivial. But finally, we did in situ TPO and quantitative TPO plus elemental analysis in special conditions. And so we were able to find the stoichiometry of this phase. So when we start from MO3, and because we make a correction of the MO2, the final composition of the material is this, MO0234, C010, H138. And this value is not totally accurate because we had problem with the presence of MO2, and because also we could not measure the H2O which was generated. So we had to make elemental analysis, and we were not happy. But we were lucky when we started from the pure bronze, which gave us the pure materials, oxycarbide, without MO2. Then we were able both to measure the CO2 peak quantitatively and the H2O peak, which was released. And in fact, the best stoichiometry of this material is this one. So when I say that this material is stable, I mean stable in terms of temperature. That means that you can leave it on in a glove box for 2 years, it will not move. But when you change on its surface the composition of the gas phase, and if the temperature is high enough, that means above 350, you can either reduce it to go towards carbides, or you can reoxidize it to go back to MO3. So that is the thing which is important with this material. But by itself, it is a very stable material, and even better, if you change slightly the composition of the gas phase in terms of oxygen, hydrogen, and carbon on top of it, it rebalances itself, and it's still a good catalyst by changing a little bit its stoichiometry. That we have made tests, but I have no time to explain that. Now I would like to go to some catalytic application. Well, as you have seen in the second transparency, when we make the preparation by doing treatment by eneptane and hydrogen, you had a very high selectivity at high conversion. And inside this selectivity, we found that we were only branching and no aromatization. So that means that it could be very interesting as a catalyst for reforming. So that's the first thing we wanted to look at. Then we shall look at the second thing, which is very important, the selectivity versus conversion. When you take conventional bifunctional catalyst, you know that the selectivity is decreasing when the conversion is increasing. We shall look at that. Then we shall look at the sulfur-nitrogen tolerance. And then we shall look at another example, the iso-dewaxing. And finally, we shall compare for this reaction zeolites and molybdenum oxycarbide. And finally, at the end, we shall look at other examples of application, if I have time. Sorry for this table, it's a bit too many things on it, but I will try to simplify. So we have compared in more or less the same condition, only temperature is changing. the bulk molyoxycarbide. Molyoxycarbide supported on silicon carbide. There, I would like to pass a little time on it. If you want to prepare this oxycarbide on a conventional support, like alumina or silica, with a support which contains oxygen, it's almost impossible. Because you have oxygen which are shared by the molybdenum oxide and the support, and they block the process of transformation. If you have a support which does not have oxygen and which makes a nice dispersion like silicon carbide, high specific surface area silicon carbide that we are preparing for the program, there you can make it. Then we have compared these two catalysts to conventional platinum and gamma alumina and a more acidic and selective catalyst, which is a platinum on beta zeolite. And you can see two things. First, that forget this one because the results are exactly the same between the bulk and the supported except the rate. You see, by supporting and dispersing, we get a much higher rate, which was normal. But when you compare the oxycarbide to the conventional bifunctional platinum on gamma alumina, you see some differences. The first differences is the selectivity. Oh, there is a problem there. That's a cracking selectivity. It's not the excuse me, there is a mistake. It's not selectivity in C7, it's selectivity in cracking. So you see we have a very high selectivity at conversion of 20% for moly. The same thing for the beta zeolites, but the selectivity for isom on platinum gamma alumina is known to be not very good because we have quite a lot of cracking. Other differences, if you compare these two, it's in the amount of cyclic and aromatic. You know that on the conventional acidic gamma alumina, you get quite a lot of aromatic cycles. On beta zeolites or on this oxycarbide, you have almost no aromatics. You have no aromatics, you have a little bit of cyclic, but it's traces amount. And the cracking is different. And that is important. You see, when you use the oxycarbide, you have mainly internal hydrocracking. When you use beta zeolites, you have not only internal cracking, but other parts of cracking. When you use beta zeolites, you have mainly the acidic cracking, the internal beta elimination. Well, what was interesting, in fact, so we have seen we have no, we can make branching without aromatics, but that is not very new because the platinum and beta zeolite is able to do it. But what is much more interesting, and then we go to NCA, but it's just as an example. When you take the conventional platinum on beta zeolites, which has a very high branching selectivity without aromatics, the problem with this bifunctional catalyst that when you increase the conversion, the selectivity drops very severely. And you see when you arrive at almost the thermodynamic equilibrium here, you have 20% of selectivity. The great advantage of the oxycarbide, which is supported in SiC on this example, that the selectivity remains very high, even at very high conversion. How can we explain that? I have what, 10 minutes still? No.
Well, we started a bit late because we haven't covered of
So the explanation is the mechanism. On the conventional bifunctional catalyst, we have first the dehydrogenation of the platinum particles, then we have the protonation, and at this stage we have the problem that cracking is possible because we have very stable intermediate carbocation in the cracking process, and it is particularly true when you started to branch a lot these hydrocarbons because you have more opportunities to make these carbocation which are very stable, so you favor these routes. And that explains why when you go to very high conversion, you increase the branching of your hydrocarbon, and you increase the possibility to crack. That's why the selectivity falls down so quickly. Or you do the isomerization by this way. On molybdenum oxycarbide, the mechanism is completely different. And that was already proposed in the PhD of Ribeiro, these mechanisms, which is that they have with Buddha called the metalacyclobutane mechanism. You get, that's a site, you get the formation of a metalacyclobutane ring there, and then you have the opening, formation of a carbene, formation, absorption on polyolefin, you have a free rotation around that, and you have a reformation of the metalacyclobutane, and you're going back to this one.
So you see, in this case, you do not need any acidity to make the isomerization. And that explains why, in fact, the only possibility to make cracking when you have this mechanism is to increase the pressure. If you increase the hydrogen pressure, you will hydrogenate the intermediate and you will increase the cracking. And that we have checked, we have done it. It's very clear, all that has been published. One thing which is still not published that I have to publish that we have discovered in other studies that I will present later, that this metallocyclobutane can be extended to bigger cycle. We can make metallocyclopentane and metallocyclohexane, which will provide the same sort of thing, but instead of branching with a methyl, we shall branch with an ethyl, with a propyl, etc. And we shall see that in a minute. So we just check about this acidity, and you see the conventional platinum betazeolite by ammonia PPD, and you can see the strong acidity, the very known acidity of, and you can see that for the hemo-oxycarbide, the acidity is very weak, and it's almost impossible to detect any absorption of NH3 in this material. Well, so second advantage, so first advantage, during the isomerization, we don't make aromatics. Second advantage, because we have no acidic mechanism, we can go to very high conversion without cracking. And we have a third advantage, which is now the sulfur tolerance. Because these oxycarbides are more or less stabilized by the presence of carbon in the structure of the oxide, sulfur has difficulty to enter in the structure. And not only that, sulfur molecules seems to do not absorb very well on these materials, because if you take thiophene, for instance, and there is the example, we run without thiophene 0 ppm of sulfur, and we have the rate 1. They are relative rate. Now we put, let's see, 30 ppm of sulfur, no effect. We put 120 ppm of sulfur, no effect, still with thiophene at 6 bars total pressure. And we have been we begin to see a real effect on the activity above 500 ppm of H2S, which is quite thiophene, which is quite high, in fact. When you do the same experiment with conventional platinum betazeolite, you see you have the rate 1. As soon as you introduce 30 ppm of sulfur, you get that. And when you go to 120, you see you lose half of the activity of your platinum channel, even inside the zeolites, which protect partially your platinum from sulfur. And if you look at the lecture that Michelle Touvel gave yesterday, the keynote lecture yesterday afternoon, she was talking about iridium and platinum, etc., catalyst, and we have done also the same sort of comparison with iridium. With iridium is even more catastrophic, the effect of sulfur. Yes.
Pardon?
To rush away.
Well,
So, fourth advantage, sulfur tolerance. Now, nitrogen tolerance. So you see the nitrogen tolerance is also very good. 2 ppm of nitrogen on the carbide, 2 ppm on zeolites. You see very immediately the nitrogen elements was given by piperidine in the flow. There we have 10 ppm, and then we have 10 ppm for platinum, that's for moly. Why we have a decrease there of the activity of moly? It's because these nasty nitrogen molecules make coke on the surface. Not because they poison the acidic function, because we have no acidic function. It's because they make coke. And we have also found, demonstrated that in these papers, which is published now. Well, now I would like to pass quickly to this NC16 isomerization, or to simulate dewaxing. So what is very important when you have utes, if you want to get good utes, you want to have a low viscosity or a high viscosity index, and you want to have a low pour point in order to do not have crystallization of your oil when the temperature is going down. So nasty products are these N-paraffins. And when you branch these N-paraffins, you decrease the pour point. You can see that from there, going to there. One thing which is interesting and not very well explained, that if the branching is at the end, it is less effective than if it is in the middle. But it is but if you increase the branching, it is becoming more and more effective. But the problem is that going to there you do not change the viscosity, which is nice because that has a very good viscosity. But when you branch too much, you begin to increase the viscosity that you do not want. Another thing which is even better, instead of making mesyl branch, if you can make long branch, 1 or 2 long branch, there the pour point is very much affected, but the viscosity is not affected, and that is very nice. So in fact, a very good catalyst for doing the isomerization, dewaxing, will be a catalyst which will be able to branch, not too much. I mean, it could branch quite a lot, but not too much. But with long branch, that would be better, and particularly with the short branch, to put the short branch in the middle. And the time is running short, I will try to go very quickly. So we have compared oxycarbide, platinum on SAPO 11, platinum on ZSM 22, because these one are processes which are well known in the industry for doing this reaction, and platinum on beta zeolite to compare with a very acidic catalyst that was made in a slurry with an excellent mass balance. So, if you look first at the very acidic catalyst, platinum on beta zeolite, we reproduce what we have seen on C6 and on C7 and C8. The selectivity dropped with the conversion, very low. The monomethyl branch is more or less constant all along, and the multi-branch containing 95% of dimethyl groups is going down. It's quite high at the beginning and going down. I will not talk too much about this simulated. The curves are simulated because I have no time. But that will be published soon. I'm writing the paper at the moment. Then we go to the SAPO 11. There we introduce in the system the constriction of shape selectivity due to the SAPO 11 structure. And you see immediately that the selectivity remains quite high because we do not crack too much at high conversion. But we make mainly monomethyl. And the multi-branch products which are made there are almost exclusively dimethyl products. Then we go to ZSM22. There it's also very interesting, but more or less the same thing than on SAPO. You have a high selectivity, even if the selectivity is dropping at the end. You have almost no multi-branch product all along. Multi-branch started only after 50% of conversion, really significant, 10%. And they are exclusively dimethyl molecules and external on the end, on the position 2 and 3 on the both ends of the molecules, which are not very nice for the pour point, as you remember. And now if you compare that to the oxycarbide, we have a complete change. Selectivity high, as you can see, as we know already. But what is very interesting, that at the end here, if we stop here, we have 60% of multi-branch, almost only 30% of single branch things, molecules. And in this multi-branch, 30% are ethyl and propyl groups and longer chain than the methyl. So that means that this catalyst should be very interesting for doing the iso-dewaxing. That I will pass quickly because I have no time. So that's the simulation we did. We did a double simulation. Just very quickly, the model was there. And what we observed, in fact, that the rate of cracking of the iso or the multi-branch molecules, the single branch or the multi-branch, these rates of cracking are very low on oxycarbide, K3 and K5, and when you compare to the other acidic, it's quite high, except on the ZSM22, because of the constriction of the zeolite. Well, we went a little bit further, and what we did, we make a two-step process. The initial composition is 0, 0, 0, as you know, no conversion, total, okay. Then the first step, we did 90% of conversion of this N16 on molyoxycarbide. We get 81% of selectivity with 22% of monobranch, 29% of multibranch, including 33% of ethyl and propyl. And then this product was sent on PT ZSM22, and because ZSM22 cannot enter in its channel the already multi-branch molecule, we can finish the product much better, And we can go up to a total conversion of 98 with selectivity of 84.4, etc. You can do that. If we do the same reaction on one step on PT ZSM22, at a more or less same conversion, even at lower conversion, you see it's catastrophic, the result. We have only 59% of selectivity and with almost no SI problem.
2 minutes more.
Yeah, so that I will skip on that. That's the cracking made on these two. You see the cracked molecule which remain, because we still have cracked molecule. It's much more interesting with the carbide than with ZSM22 because it's not big molecules and branch. We have other applications, very quickly. The other applications are direct dehydrogenation of alkanes, for instance, butane into butenes and isobutenes. I will show you that later. Nanostructure, nanoreactors, methane activation, dearomatization by hydrogenation and ring opening, the same sort of things that Michel Touvel was quoting yesterday. That is just an example of the direct N-butane dehydrogenation. You see the selectivity is very high. The conversion is significant and rather stable after a while. And if you look inside the selectivity, what is very interesting is that directly from N-butane, we make quite a lot of isobutene, the other butenes being here. And there are very few catalysts, and as far as we know, there is no catalyst at the moment able to do that, except the oxycarbide. And some of the examples of what we can do with carbides, now it's more exotic. We have microtubes of molybdenum carbides, and we are using these materials for other applications. Micro, it's micro, you will go later in nano. So there we have microtubes of vanadium carbides, so that also we can do now. There we have nanotubes. So I have not produced nanotubes of molybdenum carbide or vanadium because we still do not have a nice picture, but these are nanotubes of silicon carbide made by the same process. You see these ones are quite big, 90 nanometers internal diameter. These ones are more interesting. You see something like 10 nanometers, 100 angstrom of diameters inside, and it's pure silicon carbide nanotubes. Always made by the same synthetic method that I was talking at the beginning of my talk. And so we arrive at the end, rushing a little bit, and I would like to thank quite a lot of people. First, different PhD people in Strasbourg, and particularly Koum Famou, who is now a permanent staff in my group. He has discovered the oxycarbide, by the way, because he was a very patient and very good guy, and he is still there to try work. These people have done their PhD on different applications of these oxycarbide. Elina in Helsinki, not in Strasbourg, has been working on dehydrogenation with Baudouin. I have had Ted Oyama for quite a while in the lab, helping us a lot. Postdocs, Ed Beacon from Trondheim, and Dior from Oxford, and other people who have participated at this different project, Ruti Kranz-Schumann, Jean-Guy, Professor in Strasbourg, Claude Crouzet, who is retired now, and Sylvain Anser, who has helped us a lot with the zero lights business, who is now should write excellent movies. So thank you for your attention.
Thank you very much, Mark, for some very nice, interesting, and in some ways quite provocative work. I think because we started a little late, we really don't have time for questions, although I have one or two, but I think perhaps I ought not to indulge myself. But I wonder, you know, if people are really keen to have questions and discussion, we might perhaps do it at the end of this session. So, Mark, thank you very much.
So, you know,